Okay, cool. Yeah, so today let's talk a little bit about, well, to start, we'll talk about Fubini's theorem. So that says if I have functions going from basically two spaces to another, then I have like a natural like product measure on these guys, which usually is represented like a tensor product like this. And Fubini's theorem, all it says is when I integrate over the whole space, and I view this as a product space of x and y. So this is now just a function on a bigger space. And I look at this. Normally, you don't write the tensor, this product. This is going to be the same as the iterated integral, right? F of xy dx dy. And here I could have flipped. So they could have been either I integrate in dx first or dy. So that's the content of the theorem. It says this. And Fubini is just under which circumstances does these two equalities hold? So one of the things that's important to check when you do this kind of thing is so part of Fubini's theorem says that when I look at this function, f of xy as a function of y, this guy is measurable with respect to y, right? So this guy is measurable, and it does something nice. So one of the so this is measurable for almost every x to make sense of these integrals on the inside, right? So for example, if I look at this function, I need to make sure it's measurable in order to define these quantities, right? So it turns out that this is not always true when I can flip the range of integration. I need some constraints on f. So in particular, for Fubini, what I have is I assume that my function is L1 on the product space. So if I'm L1 on the product space, then this function is measurable and in L1 of Rd, right? And I can flip. So this is what I said before. Okay, and so this is actually a really fundamental condition. And it ends up being that if I wanted to replace this by L1 of, for example, I work on a product space X cross Y, and there's some measure d nu tensor d mu, where this guy is a measure on this space, and this is a measure on this space, so mu is a measure on this space, then the theorem also works, right? Where instead of doing dx dy, I just look at d nu d mu, right? But one of the conditions you actually need here, if I work in a more abstract setting, is I need sigma finiteness of these measures. And this is kind of apparent in the proof because you're doing certain types of approximation arguments that fail when I hit an infinite quantity. So if I'm not a sigma finite measure, that means I can't approximate the measure by a sequence of finite measured things on the whole space. And so if I'm not sigma finite these measures, this theorem actually fails. Another way this theorem fails is if I'm actually not in L1, if I kind of oscillate too much, for example, then I can't do this. So those are the two scenarios you need to look out for. So I'm just going to say in general, for general measures, need sigma finiteness and some integrability condition. Okay, so this is really all you need to know at the moment for this. I'm not going to go over the proof, but this is Fubini's theorem. There's another version called Tonelli's theorem, which works for specifically non-negative functions, right? So here, all you need is some measurability condition. So here, all you need is measurable and this condition that I'm positive. And I can have the same statement. And again, the same thing about if I go to general measure spaces, I need sigma finiteness still holds. But I don't have to care about oscillations or being in L1. So all of these quantities, if f is positive, they could all be possibly infinity, but if one of them is infinity, then they're all going to be infinity. So if f is not integrable, then all the above equations are equal infinity. Right? And then it still makes sense. And the reason you can do this is you have this idea that if I'm a measurable function, I can approximate my set as a sequence of increasing simple functions, like a linear sum of increasing functions. And on each of those increasing functions, I know what to do. They're characteristic functions of cubes or rectangles in general. And so I'm allowed to take somehow a limit from below to go up towards this function to define all of these quantities. So yeah, and actually when you're ending up showing these types of things where I flip integrals, you prove Tonelli first, and then you can prove Fubini by looking at the positive and negative parts in some sense. Okay. So this is Tonelli. It works in general. Let's see. Okay, and here's the last little thing, which is just an application of this idea of like flipping integrals in a particular way. So what it says is, I call it the layer cake formula. And the reason it has this name is, let's pretend I have a function that looks like this. And I want to understand the integral of this function. So this is f of x, this is x. In order to do that, what I start doing is I start cutting off regions. So for example, I have this. And then I look at how much area I have above this curve, and I sum it up, right? And then I keep doing this. I keep kind of building up little cubes to figure out how to approximate my function. And the continuum version of this is exactly this formula on the right-hand side, right? So I look at the measure of the super level set above lambda, and then I integrate from lambda going from 0, which would be, so if I'm moving around lambda, so this will be like a lambda 1, this is a lambda 2, lambda 3, right? These are each of the levels. So I calculate the measure of this set. So this is a domain in the X space. And then I multiply it by a particular weight to capture this LP quantity. So if P is 1, this weight doesn't appear, and I'm just integrating this guy. But let's go ahead and show it. So if I look at the the right-hand side, so right-hand side, I can rewrite this quantity as being the integral over RD. And then I want to rewrite this as the characteristic function of f of x less than or equal to dun, 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 lambda. Oh, yeah. So what I want to do is the following. Okay. I'm thinking about it more like this. So this number here, I want to view as being the integral from f to the p, right? And this is 0 of the function, let's say, d lambda. Great. Can everyone agrees that that's, if I just integrate that quantity, right, I'll get f to the p. So I'm introducing a second integral so that I can use Fubini. Okay, so if I do this, I want to rewrite this as being the integral over RD, the integral for something that's just on the whole space, on the whole domain. So lambda is a real number and it's positive because f is positive. And then I'll introduce the characteristic function here. So this is the characteristic function of lambda less than or equal to f to the p of x. Right, this is of x. And then I'm integrating d lambda dx, like this. Okay. But I know by Fubini, I can flip this quantity, right? So I know that this is equal to, by Fubini, actually Tonelli works here, so I don't care about integrability at all. But I know the whole thing is measurable. So Fubini if Tonelli. This is going to be the integral from 0 to infinity of integral of RD, and then this characteristic function. And this will be dx, and then d lambda. Okay. So let's look at this characteristic function a bit. So if I'm integrating now dx first, right? Well, what am I integrating the set function over? So I'm really figuring out the points of x such that this guy is greater than or equal to lambda, right? So I'm flipping perspective somehow. So if I do that and I integrate correctly, what I'll end up getting is a function. This will be the measure of the set of x such that this is the set of x such that lambda is less than or equal to f to the p of x. Okay. All good so far? Okay. And the last little step, you guys can check, is I let lambda prime be equal to lambda to the p. Sorry, lambda, it's the reverse. Lambda prime to the p equals lambda. And the reason I want to do this is in this formula, right, it's just they're the same scaling, right? So there's no power on f and there's no power on lambda. And I want to just introduce a pth power here.
I think you may have skipped a step here because you still have a double integral. So it should be the double integral of the same characteristic function.
Sorry, yeah, so yeah, what I'm doing is if I move this inside, you're absolutely right. So if I integrate this guy, this is just a function of x, and I'm freezing the parameter lambda. And then I'm integrating a characteristic function. So you're right. I just have to remove this. So I did 2 steps in one accidentally. Is this better for everybody? Okay. So if I end up doing this, I can shrink this down. Then what I get is exactly the right-hand side. I'm not gonna do this like a change of variables thing, right? Because d lambda prime to the p. So if I just take the, do the standard calculus thing, this is d lambda. Okay. Okay. Yeah, I'm just gonna leave that there. Okay, so this is the layer cake formula. It ends up being useful in some problems just to think about, because what you're doing is instead of measuring the LP norm of the function, it turns your problem into considering things about super level sets, right? So it's useful whenever you see a problem like that, and especially in terms of integrability, because this holds for all measurable f. So if I have some quantity that's like easier to calculate, in terms of the super level sets, I might use this theorem. Okay. Does anybody have any questions on this or Fubini so far? Okay, great. So up next, I wanted to actually go through, this is the one of the few proofs that I'll go through in the class of the Lebesgue differentiation theorem. So what the Lebesgue differentiation theorem says in short is that when I look at a function, right, and it could be some like wild function f of x that's measurable. So this is measurable. The idea is I want to understand what happens to averages. So let's say I take a ball centered at x, so this x here, and I want to look at what happens to the average over this ball of my function, right? F of y. Y. You would expect if I'm a continuous function, right? If I average over a particular interval like this would end up being kind of the average. Then this guy should converge as the radius of the ball goes to 0 to f of x, right? If f is continuous. But it ends up being that, so this is just true, and you can just check this by continuity. But it ends up being true also for L1 functions, L1 loc functions. So functions where whenever I restrict myself to a compact set, I'm integrable. Right? So any bounded function does this. Any other thing that's like reasonably nice where I can define an interval does this. Okay, and so this is what Lebesgue differentiation theorem tells you is even though I could be a potentially rough, just L1 function, I still get this notion of convergence of the averages as the averages go to the radius of the balls goes to 0. Okay, and so the actual formal statement is this: if I have an L1 loc function, then for almost every point, and these are called Lebesgue points, we have that the limit of the radius, the ball of radius r around x, if I average f on that point, then I get f back, right? And it turns out actually that this is equivalent or can be generalized to when I look at the difference among 2 points. So here I'm integrating in y and x is frozen. And I'm looking at how far do I deviate on this ball on average from my middle point, right? And in general, you can generalize this to whatever class of sets in RD that satisfy a Vitali covering lemma. So these balls can actually be, for example, they could be rectangles with bounded side lengths, side ratios. So in particular, I'm not allowed like very degenerate rectangles, or for example, ellipses with bounded eccentricity. Okay. So who, just as like a show of hands, who's seen this theorem before? Okay. Yeah, it's really kind of like to me, it feels like a natural thing to consider in some sense. I'm like looking at averages of things. Okay. You end up using this in geometric measure theory a bit if you end up getting interested in that area, because it gives you a nice representation of your function, actually, by looking at averages instead. Okay, so what I want to do for today is actually, well, the 40 minutes that we have left is to prove this theorem. So let's think about how we would do this. Okay. Oops. So in order to understand this theorem, we need to do the following thing. So yeah, a page. So in order to show this theorem, the one set we need to check, notice there's this condition that for almost every point, we have some sort of quantity. So whenever I read this type of thing, my first instinct is actually to define what set I care about, right? Because otherwise I don't have anything to talk about. So in particular, so this is the idea of the proof. And then we'll need some lemmas later, but I just wanted to sketch the idea. So first, it's true. I just want you to know it's true for continuous things. So if I take a continuous function, like I said before, in this theorem, and I look at averages like this, you can actually just check that I get the correct thing. I will converge everywhere if I'm continuous. So that's one thing we want to know. And also I know for a fact that things that are in L1 or L1 loc, I can approximate them sufficiently well within the L1 norm by continuous functions. So what this kind of should lead you to think of is approximation by these functions in the norm we care about. And so this is going to be an L1. Okay. The second idea of the proof, okay, first, we should have an intuition that I should be trying to reduce myself to the case of continuous functions. But how do I actually do that? So in order to do that, define E, and I'm going to pick the level set E alpha or E lambda. Oops. And this is going to be the set of things where my condition does not hold, right? So this is going to be the set of X in RD such that, and then I take the lim sup over, let's say, balls going to 0 that contain X. And then I look at the average, right? The thing I care about. And let's show the stronger version. So let's show this version. So if I look at B, F of Y, F of X, dy. And I want this to be, if I'm trying to look for the set, I want to show that something happens almost everywhere. I want to show that the complement of whatever condition I had, that set defines a set of measure 0 or a set of very small measure. So the set where my theorem does not hold is exactly the one where I'm greater than that. Does this make sense? So if I check, so the idea, I suppose we want to show the theorem that the measure of E lambda equals 0 for all lambda greater than 0. And that would show our statement of our theorem. Okay, so let's start working through how we would actually think about that. Okay, add a page. Okay, so let's go back to here. I have this as my set. Okay. So let's try and combine these two ideas together. Let's first think about how I can rewrite this thing in terms of continuous functions. And then when I insert a continuous function into my approximation, I pick up an error term associated with trying to control this quantity, right, by approximation. So what you end up wanting to do is kind of using triangle inequality in a sense. So let me write out exactly the way I'm thinking. So I care about the average, and I also care about this, right? So this is exactly this quantity here, but not an absolute value. Okay, so what I can rewrite it as is I want to compare it with a continuous function. So let's say g continuous, such that f minus g in L1 is small. So I rewrite this as, okay, instead of comparing the average of f, which I don't very much understand, I want to consider f compared with another function, this function g. So it's g of y dy. And in order to consider this difference, I pick up one term, which corresponds to a term which I like, g of x. So this is a good term. Good by continuity. G. Then there's going to be one extra term. So this is g of x minus Okay, so I've just added and subtracted G in a funny way. Okay. So this one, question mark, this one is hard to deal with. The reason this is hard to deal with is because I have very little structural understanding of this object, right? Just so like F is still unknown, right? And G is continuous. So this whole object, all I know is that it's like integrable in some sense. So I need to somehow deal with this term. This is kind of the hardest term. So this is what we end up using what's called the maximal function for. So this term, use a maximal function. This term ends up being not so bad. Okay. Okay. If I've set up this kind of thing, if I rewrite this expression in terms of the sum of three terms, which I'm trying to understand, I can actually use it in the set E alpha by triangle inequality, right? So by triangle inequality, I know that this term, when I rewrite it like these three expressions, when I do triangle inequality on each of these parts, it becomes like an upper bound, right? So it's still bigger than lambda. So what I need to do is I check actually that the following holds. So E lambda is going to be contained in the set where each of these things is individually greater than lambda over a third, right? So this guy is contained in the set where the lim sup over b going to 0, bx, b containing x of this guy, y minus g of y, is greater than lambda over 3 dy. Union, and then the rest of the functions, right? So this one's the good one. So this is kind of like the average of the continuous function. B of g, y minus g of x is greater than lambda over 3. And the last one, so this one's g of x minus g of f of x greater than lambda over 3. Okay. It ends up being that this term, I can just bound by Chebyshev and measure, right? So this ends up being, if I do Chebyshev, this is going to be 3 over this times this guy, f minus g. No 1. Right? But we said I'm fixing lambda to be some positive number. And I already know I picked g so that it's a very nice representation of f, but just a continuous one. So I actually know that this guy is bounded by 3 epsilon over lambda, which goes to 0 if I freeze lambda and take epsilon to 0. So this time I don't have to worry about. So make this like a green check mark, right? Because I'm trying to show that the measure to be lambda 0. I've showed this little bit. It just goes to 0 as epsilon goes to 0. Also, this one, we know by continuity that this will hold also, right? I'm missing the lim sups, but since my theorem holds for continuous functions, I also know that this has measure 0 for any lambda. Okay, and so all we need to check now is this one. Okay. Does the reduction make sense so far? Does anybody have any questions? Okay, perfect. Okay, so let's go and try and figure out what this red term is. How do I actually deal with this? To do that, we define this maximal function. So it's called the Hardy-Littlewood maximal function. And what I want you to think of is instead of an f here, really what I'm thinking about is like a f minus g, right? It's like an f minus g. Because that's the term we want to control in the other inequality. So this ends up being somehow like the worst object. I define the worst object and try and control it. Okay. So in order to do that, I need this thing. I'll just remind you of Vitali's covering lemma. Because in some sense, what I'm doing is when I check this condition, this is a very infinite thing I'm taking a supreme over, right? It's not like a countable collection of balls. I'm saying for all balls containing X of a certain type, for example. That's like a very uncountable set. It's like hard to deal with. So I end up needing to understand these collections of balls that I get by something simpler. So Vitali says that if I have G being a collection of these balls, which have, for example, uniformly bounded diameter, then I can find a countable disjoint collection of these balls such that it still covers when I increase the diameter of the balls by 5. Okay, and this is like a fundamental little trick. Basically, if I have a covering lemma like this for some family G, then it ends up being that I can bound my maximal function in a nice way. Okay, so let's go through. So this is kind of the end thing I want to show. So this is the Hardy-Littlewood maximal inequality. So what it does is it tries to understand this maximal function of my f. Again, this is, you think of it like f minus g in our proof, right? So I want to kind of control this quantity. And because if I think about it like this is f minus g, I know that this guy's small, right? In our theorem, because I'm trying to approximate it in L1. So I know I have something that's small in L1. If I can just establish an inequality like this, I'll show you how it proves the theorem, the Lebesgue differentiation theorem. Okay, in general, this type of inequality. If you view M as being an operator from L1, so it takes in an L1 function, and then I measure super level sets of this thing, right? If I move this lambda to the left-hand side, that's exactly the weak, if I take the supreme over lambda, this is the weak L1 norm of M of F. And by saying that the weak L1 norm of M of F is bounded by a constant depending on F in L1, just says that this mapping is continuous, right? Okay, it ends up being not linear because it's not, this thing involves an absolute value, but it's what's called sublinear. So it's the maximal function is a sublinear bounded operator from L1 to L1 weak. Okay, so let's go ahead and show this thing and then put it all together to show the Lebesgue differentiation theorem. So proof of Hardy-Littlewood Sobolev Hardy-Littlewood inequality. Okay. So the first thing we check is I have to understand the set of X such that MF of X, which is positive, is greater than or equal to lambda. Right? So I want to show that I can get a 1 over lambda times the L1 norm of F. Okay. So let's pick, so I want to show that this guy is bounded by something. To do that, let's understand the set better. So pick an X in here. Now, for technical reasons, I'm going to look at this just because it makes it easier. But if I look at an X in here, well, M of F is defined to be the supremum over all balls containing X of the average integral B of absolute value of F of X dx. So if I'm greater than lambda, that means that there exists a ball Bx such that Bx contains X. This is 0.1. And I get that 1 over Bx integral over Bx, f of X. Sorry, I'm going to replace notation a little bit. This is going to be a dummy variable y, right? So I'm really integrating over y dy. And I can actually pick one so that this is still greater than lambda, right? Because the soup's kind of continuous in this way. Okay, and let's rearrange this a little bit. So I have the integral of b of x f of y dy is greater than lambda times the volume of this ball. Okay, so as you can see, I get this collection of balls bx, but it's like infinite, right? Because each x, like for every x in Rd, I get a ball bx. So if I look at the collection G bx such that star holds, this ends up being a thing I can apply vitality to. Okay, so let's check. What does it mean I get a vitality covering of this? So if I apply the theorem, it says that, okay, if I look at the union over all these guys, right? This covers this set, MF greater than lambda, right? Because I mean, it's a if then statement. If X here, then X is in the ball, right? And if I union over all possible balls, then I'm contained this way. Okay, so that one's pretty easy. Vitality tells me that I can look at a countable union of these guys, and I'm just going to call them BK. I just have to increase the diameter by 5. So there exists a sequence BK in G such that this happens. Okay. Now I have to measure this countable union on the right-hand side. Okay, so how do I do this? Well, I end up just using the star quantity, right? So if I take the norm of all of these guys, or the measure of this set, this is going to be less than or equal to, I can't actually measure this in a nice way. Like this is just some set. I'm not even sure it's measurable, but I actually have this quantity, which I can measure. So I'm just going to use the subadditivity of the measure to get 5. And if we're working on RD, I get 5 to the D. This will become a sum of the measures of BK. Is that clear to everybody how I got that? It's just subadditive.
Can I ask a question?
Sure.
So to apply Vitali lemma, do we need the diameter to be uniformly bounded? And do we
Good question.
Do we
Yes.
use star, like the star inequality with integrability of F to show that?
Let me think about that. You're asking if this quantity shows that the balls are bounded. I don't think it.
Yeah, like thinking like by contradiction, if it weren't, then the inequality couldn't be true. Maybe.
So if I am integrable, then when I take the diameter of the ball to go to infinity, right? This guy converges to a finite number, but this guy is always growing, right? So actually, you're absolutely right that if I'm in L1, then this guy being bounded forces that these balls have to be of bounded size, right?
Thanks.
Yeah, so you're exactly right. There is an edge case when I have, I can't apply vitality if somehow my spheres are huge or like they're degenerate in some way, degenerate to infinity, right? Because that's one of the conditions of vitality. They need to have, uniformly bounded diameter in certain cases. You can get around these things. There's this thing called the Besicovich lemma, which is a version of this, but I don't want to go into that so much. Anyway, so I know that these guys I can apply vitality to. What our conversation. So I can apply vitality. Okay. Good question. So now I'm trying to understand this super level set. I've turned it into something I know, and I just apply star now. So star tells me that each of these guys is bounded by 1 over lambda times this, right? So I get by star, this is 5 to the d, and then I get a 1 over lambda. And then this will be the integral on bk. Some k goes from 1 to infinity of f of y dy. Right, and this is just using star. Okay, but I know actually that all of these balls are disjoint. That's part of vitality, is I've picked a subcollection which is disjoint. So I get that I can actually move. So this sum is the sum over disjoint balls. So this is going to be equal to the integral over all the union of all the balls, right? But that's still less than the measure of the whole set. So I say that this is less than or equal to 5d lambda times the integral over the whole set, f of y dy, which is equal to 5 to the d lambda L1 norm of f, which is exactly the inequality we wanted to show. So in a word, there's 2 steps. I have to find the condition which gives me a vitality cover, right? I need to get a disjoint subcollection. So I can, this needs to be just some finite number. So it's just some constant. And I need the BKs to be disjoint. So that's what I was using. Okay. So I've proved the Hardy-Littlewood maximal inequality. And let's go back and prove the differentiation theorem. So if I'm back to here, right, I now have this quantity. I'm just going to go and copy it. So the other ones we already knew how to take care of, right? So copy. Okay. And I'll add a page. Great. So this is the term we have now. It ends up being, okay, so I know that this quantity, oops. Oh, no. This guy is bounded above by the maximal function of f minus g at the point x, right? Because I'm taking a soup, and then this one's just smaller because I'm taking b to go to 0. I still have this soup. So what this shows is that this set is contained in the set of the super level set of this difference being greater than lambda over 3. Now, what I get is there's going to be, if I go back to look at E lambda, the original thing I cared about, this is going to be less than or equal to, what did we have? We had a term coming from this maximal inequality. So there'll be an m of f minus g, x greater than lambda over 3. Then I had a term corresponding to, that's actually the empty set. Yeah, it's the empty set. So this is the term corresponding to where I just look at the average of a continuous function and I compare it to its center point as the diameter goes to 0. So there's a term that's like plus a 0 here. Plus, and then the last one was this term I could control. So f minus g by Chebyshev. So I had f minus g at the point x greater than lambda. But I know that f and g are close in L1, so I had something like 3 over lambda times epsilon. Okay, and now I apply now I apply my Hardy-Littlewood sublove. so Hardy-Littlewood inequality, to get that I bound the maximal function of these guys by 3 over lambda, 5 to the d, L1 nor of f minus g. Plus, and then I had a 3 over lambda epsilon. So this guy is actually equal to some constant depending on the dimension times epsilon. And it's over lambda. So now the argument goes, take epsilon to 0. What this shows is for any positive e, this is 0 for all. So any positive lambda, this is 0. And it's a quick check to show that this implies if x is not in the intersection, let's say lambda is n equals 1 to infinity of like e of 1 over n, right? So I have a count of, I'm taking lambda to be 1 over n. Then x, how do I say this? The limit as for b containing x and b going to 0 of the average b of f of x minus y dy equals 0. So that shows our theory. Okay. I think this if this is the first time you're seeing this, there's like a couple interesting things to me that are happening. One is you kind of know what you want to do in some sense. You know if it's things are continuous, and I'm allowed to approximate things by continuous functions. All I have to do is measure how far off I am when I plug in this approximation, right? And the way you measure this is somehow with the worst object, this maximal function. It's somehow like the worst possible thing I could get in terms of upper bounds. And then you show this with this weak version of an upper bound. It ends up not being continuous from L1 to L1, so I can't do it in a strong way. But I get this kind of like weak measure theoretic version of how to control this error term, this maximal function of the difference. Okay. Any other questions? Okay. Well, I have one problem that's related to this. Yeah.
Can I just ask, out of curiosity, you said this sort of like the final results holds for any integral that you can define. Were you thinking of some other integral as well, like more general or different?
And what's so for the maximal function, you mean?
No, like the Lebesgue differentiation theorem. You said that the fact that like when we average, like the average sort of like reflects the value as the ball radius goes to 0.
Yeah.
You said that it holds for any integral that you can define. Maybe it was just, something.
Yeah. So what I mean is, so there's different variants. I guess I could talk a little bit about the variants. The one thing I find interesting, like geometrically anyway, is the simplest versions of this theorem geometrically look like this. So if I have this is the ball of radius r around x, right? And I want to understand the behavior of averages as I take r to 0 over this set, right? There's variants of it, which are, there's like an uncentered variant. So it's just, this is the one I showed actually. So B contains X. So this could be a different center point. And what it ends up being, if you have this kind of scenario, actually, I think you're still fine here. But when you get into things like, for example, rectangles like this, so you end up having to do weird stuff where I can't do a vitality thing. For example, let's imagine I have a sequence of increasingly smaller and thinner rectangles going on. So when I try and scale up one of these guys and try and do the vitality covering argument, it ends up that if they're unbounded in terms of their eccentricity, these rectangles, I can't find a disjoint subcollection that still covers, right? So people care about this a little bit, but it's kind of like an esoteric thing at this point. But there is one scenario where when I can't apply Vitali's covering limit is when I can't do this thing. Okay, cool. Let's do yeah, thank you for the question. Let's do one problem, and then I'll let you guys go. So let me find the problem first. Okay. So yeah, next time we'll talk about absolute continuity and then probably more problems. Okay. So the thing I want to talk about is it's one of the prelim problems. That's an application of Fubini, actually. So it's not to do with the maximal function. Okay, so let me just write it down slowly. So this is problem 15. In what section was this? So this is on the website of dense intersection density and limits in LP. So this is where to find the problem. Okay, so the actual problem statement is considering things on a measure space. So let X, A, which is the set of measurable subsets of X with respect to a measure mu, be a finite measure space. So what this means is mu of X is finite. Okay, so show F is in L1 X d mu if and only if the sum of mu of X and X such that F of, let's say F is positive just for simplicity. F of X is greater than or equal to N. The sum goes from N from 1 to infinity is finite. So this infinite series converges. Okay. All right, so let's try and do this problem. Does anybody have any ideas how you would start to show this kind of thing?
Well, I mean, this is an immediate application of the integral test in the layer cake formula.
Mm-hmm. Let's go through it on how to do this. So I think you're exactly right. That's like easier than what I was thinking. So if I do the L1 formula for the layer cake, I get 0 to infinity times the measure set in X such that F of X is greater than or equal to lambda d lambda. Right, and this was that whole trick of it's just Fubini, and I'm allowed to apply Fubini here because I'm looking at a measure which is sigma finite, as I was saying. So I can apply Fubini in this case. Okay, and the way I like thinking about this convergence test is this is going to be the same as I go from n equals 0 to infinity, right? Sorry, this is going to be mu of the integral of n to m plus 1 of the same quantity, d lambda. Right? Okay. And so what I get is that this guy is equal to Mhm. I want to say it's less than or equal to. Yeah. Okay, let me write it out. So it's going to be mu of the set of x and x. F of x greater than or equal to lambda. And if I go to the lower one, right, the set only increases. So if I make lambda is in the range of n to n plus 1 here, right? So it starts at n and n plus 1. It only grows bigger if I go to n, right? Because I'm considering a less restrictive condition. So this is going to be the same. It goes from 0 to infinity of this guy, and it's 1 mu of x and x, f of x greater than or equal to n. Lambda. And the measure of each of these guys is 0, right? Sorry, it's not 0, it's 1. So this is going to be the sum. And it ends up being, so I start from 1 to infinity of the thing I care about. So mu of f greater than or equal to n. And then there's the term corresponding to 0. So if f of x is greater than or equal to 0 and f is positive, this is just going to be the whole space. Okay. So this shows if I satisfy this condition, then I'm in L1. Does that make sense? It is just the integrability test. Okay. But we can also do another thing. Notice here, I kind of traded some information. So if lambda went to the bottom of this range, I increased, right? I get a bigger set. If I go to the upper range, I decrease. And it ends up, you do the same argument and I get the same quantity. So f an L1 is bounded from below by when I plug in the upper range here, so n plus 1. And then you do a little bit of manipulation, you see that, okay, that converges equivalently to if the series converges, right? So if f is an L1, then actually you can show that this series converges. Okay. Yeah, and so this is, in some sense, as you were saying, I'm just reproving the convergence test in some sense. But you got to check little bits of things to do with measures. Okay. I think that's it for today. Does anybody have any questions about this part? Okay. Well, again, we'll be having a lecture on Wednesday, so that's the 10th. Same time. If you have questions about the prelim problems, send me an email and I can maybe talk about them. And also on the 15th, I'll be traveling. So we'll be having lectures instead next week on a Wednesday and a Friday. So skipping Monday. Okay. Cool. Thank you guys.
Thank you.
Thank you.
Thank you.